Okay, as I mentioned yesterday, the middle step in doing stoichiometry is the purpose on balancing equations. There you're going to be looking at the ratio of the coefficients. In fact, let me just show you that again. Right here in the middle. So here's the reaction here after it was balanced, and then we took this middle part. So stoichiometry is three parts. Convert to moles first, ratio from the balanced equation, and then convert back to whatever you're trying to calculate from the moles. Every single one, three parts. So the purpose of the middle part is to look at the mole ratio of what you're starting with versus what you're ending with. So that's the reason why the first step is balance the equation if there is a reaction. Now, when you're reading the little write-up on the problem, these are the four things to look for to know a reaction occurred. Also, there are two labs coming up. One's called single replacement, the other's called double replacement reaction. Same thing. You're going to get a color change, bubbles form, gets hot or gets cold, or a solid forms, or a visible liquid separates out. Those are all signs that a reaction occurred. Okay, now, why does a reaction occur? Like everything in the universe, it has to do with stability. And you're going to later refine that to be stability plus randomness, which is called entropy. So if entropy increases, the reaction will happen. Also, if it has less potential energy or it's more stable, it'll happen. So those two are together. We didn't cover entropy in here. We just covered just the word stability. But it's got to be stable. Now, entropy can overcome that if it's not stability related, but that's for your next class. Okay. So as far as we're concerned, there are two parts to all reactions: reactants, products. Normally, the reactants are more unstable than the products. Otherwise, the reaction wouldn't happen. Now, in lab, we talked about another thing that goes on in a reaction. That's how fast the reaction goes. You can have a reaction happen, but it may be going so slowly that you don't realize it's happening. The example I gave is diamonds. Diamonds are pure carbon. Charcoal is pure diamonds. Charcoal is converted to diamonds under horrendous pressure and time. Guess which is more stable, the diamond or the charcoal? He knows the answer. Everyone says diamonds. Actually, the charcoal is more stable. And you're going like, we spent all that money on a diamond ring and it's going to turn to black charcoal on my finger? It'll take a long time because the reaction is so incredibly slow. You don't know what's happening, but it is happening. So it's very interesting. So that's called kinetics. How fast is the reaction going? In your next chemistry class, you're going to have a whole chapter on kinetics. It's very important. Also, it has to become more stable. So one's called thermodynamics, that's the stability bit, and the other is called kinetics, that's the speed bit. Both those are happening in every reaction. Unfortunately, if it goes super slow, like diamond to charcoal, it appears like nothing's happening, but in fact, I interviewed for a job, and that was one of the interview questions. Was talking about, and I talk about this all the time, so I was very familiar with it. But it was they said talk about the charcoal and diamond reaction. I had to do charts and all that stuff, but okay. All right, so I've developed a process to do balancing equations. And it's kind of clunky, but it's very fundamental and intuitive. And it's a little clunky. The other way to do it is a very sophisticated way using linear algebra and matrices. When I taught the class for engineers, that's all they did when they balanced equations. And they knew how to do them on their calculator and all that stuff. We're not using that one because most of you have not had linear algebra. And that's a class you take after calculus. So, okay. So let's look at a reaction, an unbalanced reaction. Let's take methane. With some oxygen and burn it. Okay, so we're going to get carbon dioxide and water. This is called combustion. A very common reaction in our world. Now, the official definition of combustion is you have a fuel, in this case it's methane, and an oxidizer, in this case it's oxygen. Because on rockets, they don't usually use oxygen, they use something else to achieve combustion. Okay, so let's look at this. Basically, what a reaction is what you start with is what you end with. So if you start with 5 marbles and you do a reaction, you got to end up with 5 marbles. If you end up with 4 or 6, something's wrong. Same thing with reactions. And we're talking about atoms now. So we're going to do an inventory of the atoms on the reactant side and the product side. So we've got carbons, hydrogens, and oxygens. Now you have to list all the atoms. You cannot leave one out. It's extremely important to have all of them represented there. Okay, now we're going to do an inventory. How many carbons on the left? And by the way, one other thing, there are 2 numbers in all reactions. There's a number up front. That's called a coefficient. Coefficient. And then there's subscripts. You can only change the coefficients. No exceptions. You cannot change the subscripts. If you change the subscripts, you're changing the molecule. We can't change the molecule. Now, the coefficients represent 2 things. It represents the number of molecules and the number of moles. Okay, so if the coefficient is blank, like these are, it's the same as 1. Now, if you want to put 1 there, that's fine. I'm just saying though, but if it's blank, it's 1. So we have how many carbons on the left? How many on the right? Okay, so far the inventory says it's balanced. How many hydrogens on the left? On the right. So we have a problem. What about oxygen? 2 and 3. So we started off really well, but things didn't go so well. Okay. So as I said before, we can change the coefficients to balance the equation. So let's change a coefficient. The one I would suggest starting with is the most complicated one. In this case, oxygen is the simplest, so we're going to leave that alone. So we can choose either methane, carbon dioxide, or water. We're going to change the coefficient to something else. Usually you kick it up to the next number, like 2. So which one of those 3 do we want to change? Water. Okay, we make that a 2. Now, once we change the coefficients, we have to do inventory again. Okay, so we've got 4 hydrogens now. We've got 2 and 2 oxygens, so that's 4. And over here on the left, we still have 2 oxygens. So what are we going to do now? We're going to add another oxygen, but we're not going to add it. We're going to change the coefficient to 2. That means we're multiplying. Now, multiplying is a shorthand way of adding. It's like dividing is a shorthand way of subtracting. Okay, so we have to, that kicks that up to 4. Now it's balanced. The reason why it's balanced, because the inventory says reactants equals product. So we're not going to have an explosion. And with Einstein, E is equal to mc squared, or m is mass. If mass disappears, it's converted to energy. And the c squared is the speed of light squared. That's 300 million meters a second squared. So a little bitty mass makes a lot of energy. Or we want to make mass, it takes a lot of energy to make mass. Okay, does that make sense, the process? Now, this process, inventory, coefficients, inventory, until it balances. This process is called guess and check. That's as analytical as it gets. Guess and check. Okay. Now I've got a worksheet. In fact, I have like 5 worksheets on balancing equations. And I have the answers as well. So those are all the answers. So let's do another one. Let's do another combustion one. Are there any questions on this process? Yeah.
So that will just be your final answer then?
Yep,
So
exactly.
you'll leave the numbers.
Yeah. Does that make sense, Aaron? From the book?
Yeah, it's a lot easier than this book.
Okay. All right, so let's burn, instead of methane, let's burn ethane. Ethane is a 2-carbon hydrocarbon. Now, if I made this C8, that would be gasoline. So when you start your car in the morning, you're making water in your engine, and it drips out of your tailpipe. So when you start your car in the morning, tomorrow morning, run around the back of your car and look at your tailpipe, and you'll see water coming out. And after a while, the water goes away. Does that mean combustion's not happening? Yeah, so what's going on?
Let the water evaporate.
Yeah, it's steam instead of liquid water. It's there, you just can't see it. Contrails from jets. Contrails are those white trails behind jets. That's the same thing. Those are ice crystals. During World War II, they had like 1,200 to 1,400 bombers towards the end of the war over Germany. And the Germans knew they were coming because of all the contrails. And those contrails also last for a long time. They just get more spread out. Now, there was a conspiracy theory going around in the 60s by a guy named Art Ball. Has anyone heard of him? He was on AM radio. He was always on starting at midnight. So whenever I was driving for whatever reason, in the middle of the night, I would turn on Art Ball. And he always had these wild stories about the government has putting chemicals in the contrails and poisoning us all and all this stuff. Also, people were hiding behind comets and spaceships and all this stuff. It was pretty funny stuff. It's fun listening in a car when you're really bored. Okay, so here we have ethane burning. Ethane is another gas found in natural gas that comes out of the wall. Mostly methane, but there's quite a bit of ethane in there as well. All right, so let's take an inventory. We have CHO. Okay, so we have 2 carbons on the left. How many on the right? 1. 6 on the left. How many on the right? And then 2 oxygens and 3 oxygens there. Okay. So we have proof that it's not balanced. Okay, so which one do you want to start on? Carbon. All right. So we're going to change the 1 here to a 2. Then we take inventory again. Okay, so that kicks our oxygen up to 2 plus 1 is 5. Okay. So the carbons are balanced, but nothing else is. So what are we going to do?
Water.
Let's change the water to 3. Okay, we have to do inventory again. So the carbons didn't change, but the oxygens did. So we have 4 plus 3 is 7. You all see how I got the 7? It isn't just one molecule. We have to do the whole thing. Okay, so the oxygens are the only thing left not balanced. So because we left oxygen last, what are we going to change the coefficient to? Okay, so let's just keep that as a fraction for now. And you're absolutely right, by the way. So 3.5 or 7 twos, yeah.
If 6 on one side, wouldn't it be 5 on it? Right, you said it's.
We have 3 waters. Each water is 2, right? So it's 2, 2, 2. That's what this says. 3 waters. Does that make sense why it's 6?
Yeah.
Each one's 2. We got 3. Yeah,
But it'll be
3. So it's, you don't add, you multiply. 3 times 2. Okay, so it's officially balanced. Now, the problem is the coefficients, yeah, over here on the right. 7 oxygens. Is that your question, how I got to 7?
Yeah.
Okay,
5.
correct. Okay, we have 2 times 2 is 4. And then we have 3 times 1 is 3. 7. Better? Okay, now the problem is, remember the coefficients are the number of molecules or the number of moles. Now we can't have a fractional part of a molecule. Can't break them up. It's going to be whole units. So like he was saying, we're going to clear the fraction by multiplying everything by the denominator, the bottom number, 2. So 2 times 1 is 2. 2 times 7 halves, 7. 2 times 2 is 4. 2 times 3 is 6. Let's do an inventory again to validate that it's still balanced. Okay, we've got 4 carbons, 4 carbons, 12 hydrogens, 12 hydrogens, 14 oxygens, and 8 and 6 is 14. It's balanced. So some teachers will tell you right off the bat, oh, I can have fractions. Put the fractions down so it's balanced, just don't leave it as a fraction. Because we can't have fractional coefficients. Does that process make sense? That reasonable? Yes. And then we check. The check is the inventory. Yeah.
But I'm a little confused how you came to the conclusion of putting a fraction there.
Because
We were at 2 CO2
and
and then
then we end up with 2 CO2s, it gives us 4 oxygens. And then 3 oxygens over here, so that's 7 total. So oxygen on the left comes by 2s. What do we multiply 2 by to get 7? Decimals, what would it be?
Decimal,
Yeah, it's 3.5, right? 3.5 times 2 is 7.
it's not a whole number that you have to make a fraction.
That's what, yeah, so now we're gonna clear that. By multiplying everything by 2. And that clears that fraction out.
I understand the multiplying by 2 to even everything out. I was just confused how you,
Arrived at 7/2.
yeah, but I get, thank you.
Yeah, and 7/2 times 2 is 7.
You have to end with like a whole number, right? That's why you do it to the bracket. You got it.
Well, you can leave it as a decimal, but you have to realize decimals are fractions.
Right, but you gotta turn it into one number.
Okay, so those are 2 examples. The first one was pretty straightforward. The second one wasn't too bad, except the fraction thing kind of came in. I purposely did ethane because I knew ethane was going to produce a fraction. Okay, so how are you guys with this? I've given you lots of practice. Now, there is this problem. Now, this page number 9 is hard. It's not as hard as extra credit. The reason why it's hard is because there's so many elements there. However, the elements can be simplified. We look at NH4. That is an ammonium ion. It's a group, NH4, plus 1. Notice we have NH4 on the right also. Notice that we have phosphate, which is PO4, PO4. We've got nitrate, NO3, NO3. And then we have lead on both sides. So we can simplify this. Instead of taking apart all that stuff, we're going to group them together. We're going to say the NH4 really is, we're going to call it X. So we're going to have X's here, Y's, Z, and lead. So let's do inventory. How many X's do we have? How many X's do we have on the left? 3. How many on the right? We have 1 on the right. The whole thing is an X. The whole thing is an X. We have 1 on the right, 3 on the left. Okay, if we put phosphate as a Y, how many Y's do we have on the left? How many Y's on the right? 4. And let's make the nitrate as Z. So how many Z's on the left? 4. And we have 1 on the right. And how many leads do we have on the left? 1, and on the right, 3. So whenever we have an ion grouping on both sides, the only way it'll work is that they have to be on both sides. If it's on one side only, can't do this process. Okay, so let's balance it now. Which one do you want to start on? Okay, what side? And that makes 3 Z's. as well. Okay, so, it's not balanced yet, so what are we gonna do next? Hmm? Okay, we've got, we'll put a 4 over here. Okay. Now that changes the x's though. X becomes what?
What?
12. How about the lead? What are we going to do with the lead? 3 on the right, 1 on the left. And that's going to change the z's. How many z's are we going to have now?
Well,
12. Okay, we've only got 3 on the right.
oh.
So x now becomes 12. And the z's become 12. Balanced. Now, had we not done that, this would have been a really complex problem to balance. This is about as hard as it's going to get, except for the extra credit. A number of people have already done that, by the way. I think four of you, I think, has done it already. All right. So with balancing equations, it's going to be an aha moment. You're going to be doing some and went, oh, I get it now. And after that, it'll be a breeze. Until that time, it's going to be frustrating for you. I've been doing this a long time. Now, why this is important is if you don't get the balancing equation right, your whole stoichiometry problem is going to be wrong. Whole thing. Because the middle step on the stoichiometry, remember, is the ratio of the coefficients from the balanced equation. So if your coefficients aren't correct, your ratio is not going to be correct, and your problem is going to be wrong. So this is as important as yesterday. Okay, so what we're going to do now is we are going to practice. Now let's look at the so the ones that are have lots of stuff in them are the hard ones. Leave those for last. Just bounce around on these guys. And this is a worksheet on Canvas under Files, Unit 4. So that's what we're doing today. And I'm going to spend a fair amount of time in class doing this. So I want you to make sure you understand this. Now yeah. Yeah. And we're not done with test 2 stuff yet either.
The equation and no.
It'll be nomenclatures, Lewis structures, balancing equations, conversions, and stoichiometry. We haven't covered that yet. And again, Unit 2 and Unit 3 are really important units. Yeah,
What day? Yeah.
Wednesday. Thursday. It's July 3rd. So we're recognizing for July 4th.
That mean no lab on Wednesday?
No. That's not- I think that's the hydrate lab for Monday, Wednesday, April. You look at the schedule. I know hydrate's the next wet lab coming up. Okay, I'm gonna end this recording.